Hello, good morning, and Happy New Year. I bid to Dr. Kok. So today we are from Group 4, Section 2. We'll be presenting about our group project for this subject, which is Industry Power System. So before we move to the introduction part, let us first begin with introduction of group members. The first one is me myself, Muhammad bin Afandi. The next one is DEVIKA, anak perempuan SIVAANANTHA. Muhammad SYAIFUDDIN bin Asli, NORAMIRAH ALYA binti Muhammad AZIZI, SITI SALWANA binti TUKIMAN, and the last one is MAHFUZAH binti Manan. So now, let's begin with the introduction part. This project focuses on the analysis of an industrial power distribution system for a medium-sized manufacturing plant. The plant receives an 11 kilovolt supply from the utility, which is tapped down to 400 volts to supply motors, lighting, HVAC, and also the welding load with provision for future expansion. As industrial operations grow, it is important to ensure that the electrical system operates safely, reliably, and efficiently. Issues such as the voltage regulation, fault levels, motor starting effects, harmonics, and also the protection coordination must be carefully evaluated. Therefore, ETAP software is used in this project to model and analyze the power system under different operating fault conditions with the aim of assessing system performance and identifying potential improvements. As for the project methodology overview, the project began with a detailed review of the project brief to understand the scope and requirements. Key system parameters such as incoming voltage, transformer rating, and load demand were identified. ETAP software was selected as the main tool for modeling, analysis, and protection studies. The methodology was structured in a logical sequence, starting from system modeling to detailed analysis. Accurate system modeling was prioritized as all analyses depend on the correctness of the ETAP model.
TUKIMAN, my metric number AE220032. Today I would like to show you about the ETAP simulation. So, as you can see, this is our single line diagram. It consists with power grid, the high voltage circuit breaker, bus bar, transformer, cable that connect the transformer to switchboard, and also the main switchboard to the load. So, and lastly, we have the motor load and another load like lighting load, welding load, and also the spare feeder for the future load. So the setting is for power grid. The connection is 3-phase. The rating is 11 kV. The short circuit rating is 250 MVA. So for the high voltage circuit breaker, we use ABB manufacturer, which is standard NSI. For the transformer, it is step down transformer. The rating, which is it step down the 11 kV to the 400 volt. The impedance is 6%. The vector group is TYN11 and earthing type is TNS system. So for the cable, the length is 30 meter and we use XLPE copper cable. Then the impedance, and then the cable from main switch to the load, we use 80 meter for motor load 1, and the others is the length is 50 meter. The type of the cable is the same, XLPE copper. So for the motor load 1, the connection is 3-phase, 400 kilowatt, and then the model, this one. Okay, then the motor load 2, 250 kilowatt, Okay. Turn up the lighting load 400 volt and 150 kVA. The welding 375 kVA. And then the spare one is 200 kVA, which is 200 kilowatt. For the load flow analysis, we can click here and then we can run the load flow analysis. So we can see at bus 1, the percentage is 100, and at the bus 3, the percentage is 94.36%, which is the losses is 5.35%. And then for the short circuit analysis, firstly we have to set the fault at the bus 1, and then we click the run previous device duty. Then we'll appear like this. Then for the bus 1, bus 3, so we have to set first and then click at the same place. Then it will appear like this. Then for the motor analysis, we have to motor starting analysis. Just click at this place and then we can just click the run dynamic motor starting. So you can see the settings here, the motor setting time slider, so you can just go to it. For the graph, you can click at the plot, this one, motor starting plot, and then you can choose which plot that you want. So click the motor, choose both motor loop 1 and 2. So next you choose lead, speed, current line, voltage bus base, and then the motor torque. Then you can click plot. So the graph will be appear. So this is the sleep graph, speed graph, current line, voltage bus base, and the motor torque. Then you can just save it. So for the harmonic analysis, click the harmonic and run the harmonic loop flow. Then we can see the THD at bus 1 and bus 3. The first order THD, third order, fifth order, and also the seventh order of THD. For protective device coordination, before we run the simulation, we have to add 3 components at each bus bar. First, we have to add circuit breaker, current transformer, and also the relay. Then we go to the protection and coordination star. Then we have to select the entire SLD. Then click the create star view. Then this is the time current characteristic curve for protective device. That's all from me. I will pass to MAHFUZAH, SYAIFUDDIN, and NORAMIRAH for explain the result of the simulation.
For system modeling, an industrial power system was developed in ETAP using a complete and well-organized single-line diagram. The utility supply was modeled as an 11 kilowatt three-phase source, which is stepped down using a 2 MVA transformer to supply the low-voltage distribution system. The transformer is configured with a DYN11 vector group, which allows a neutral point on the low voltage side and is suitable for industrial applications. A 400-volt main distribution bus supplies various types of loads, including motor loads, lighting loads, welding, and HVAC loads, as well as a spare feeder for future expansion. All feeders were modeled using SLPE copper cables, and a TNS earthing system was implemented to ensure safe and reliable system operation. After completing the system modeling, a load flow analysis was performed to evaluate the steady-state operating condition of the system. This analysis focused on important parameters such as bus voltage levels, feeder current flow, transformer loading, and overall system losses. From the results, the transformer loading percentage was checked to ensure that it operates within its rated capacity under normal conditions. The system power factor at the main distribution bus was also reviewed to assess the efficiency of power utilization in the plant. Overall, the load flow results show that the system operates within acceptable voltage limits, with no abnormal loading or excessive voltage drop detected.
Hi, my name is SYAIFUDDIN. So I will present about a short circuit analysis. For the short circuit analysis, we look at what happened when the fault occur in the system. So the purpose of this style analysis is to make sure the equipment and the protection device can handle fault conditions safely. From the result, we found that the highest fault current happened at the low voltage main bus. This is because the impedance or at the low voltage side is lower than, and there is also a contribution from the transformer and the motor. At the high voltage side, the fault current mainly comes from the utility supply. We checked a different type of the fault, such as a three-phase fault and a line-to-ground fault. Although three-phase fault produce a high current, and the other fault type are still important for protection design. And for overall, the short circuit results show the system is properly designed and the protection devices are suitable to operate safely during the fault condition. Alright, next a motor static analysis. For the motor static analysis, we look at what happened to the system when the large motor are switched on. From the result, we can see that when the motor start, they draw a very high current for a short time. This high current causes the voltage at the low voltage bus to drop, and during the starting of the motor load 1, the voltage goes down to around 74 to 75% of the normal value. Even though the voltage drop, both motor are still able to speed up smoothly and reach their normal operating system without any problem. After the motor finished starting, the current reduced and the voltage slowly returned to its normal level. The result also showed that the protections device do not trip during a motor starting, which means the system is able to handle a motor starting safely.
Hi, my name is NORAMIRAH ALYA, number battery AE220046. Today I will continue about harmonic analysis. For the harmonic analysis, the study was conducted to assess power quality issue caused by non-linear load in the industrial power system. In ETAP, harmonic order including the first, third, fifth, and seventh harmonic were analyzed, as these are commonly generated by motor drive and power electronic equipment. The total harmonic distortion or THD was evaluated at the main low voltage bus as shown in system harmonic bus information. The result indicate that the THD level at the low voltage buses are within acceptable limit based on standard power quality guidelines. The potential impact of harmonic on system performance and equipment such as additional losses, overheating, and over distortion was also reviewed. Although the harmonic level were acceptable in this case, possible mitigation methods such as passive or active harmonic filter were considered to ensure long-term system reliability, especially under future load expansion. Next is protection coordination. For this part, we analyze the protective device coordination using ETAP, time current characteristic or TCC curve. The coordination was carried out between the incoming supply protection, transformer protection, and feeder circuit breaker to ensure proper grading of protection device. From the TCC curve, proper selectivity was achieved, meaning that during a fault condition, only the protection device closest to the fault location will operate, while absent device remain in service. Motor inrush current during startup was also considered in the relay and breaker setting to prevent nuisance tripping, especially for large motor loads. Overall, the protection coordination study confirmed that the system is safe, reliable, and well coordinated, ensuring effective fault isolation and continuity of supply. That's all from us. Thank you.
For this project, an industrial power distribution system was successfully analyzed using ETAP software. The load flow analysis showed that all bus voltage levels were within acceptable limits, indicating that the system was properly designed. Transformer capacity and feeder loading were also found to be adequate for the connected loads. Short circuit analysis was carried out to determine fault current levels, which helped in selecting suitable circuit breakers. Motor starting analysis showed the impact of high starting currents on system voltage, highlighting the importance of considering motor starting conditions during system design. Harmonic analysis identified power quality issues, emphasizing the need for harmonic assessment in modern industrial power systems. Proper protection coordination ensured selective fault isolation and improved overall system reliability. From this project, we gained practical experience in using ETAP for modeling and analyzing power systems. We also improved our understanding of load flow, fault analysis, motor starting, and harmonic studies. In addition, this project enhanced our problem-solving skills, teamwork, and technical report writing abilities while providing valuable exposure to real industrial power system applications. Thank you.